In this lesson, we are going to look at the free and forced oscillation of electromagnetic waves. The learning objective for today's lesson is you are going to be able to know and describe the forced and free electromagnetic oscillations. Let's describe the oscillations. If you have, for example, a mass spring system, a mass connected to a spring, it oscillates back and forth on a frictionless surface. In this case, there is going to be an amplitude of the oscillation. There is going to be a maximum displacement from the equilibrium position. This is where x is equal to 0, and here will be the amplitude of the oscillation, and it will move back to somewhere here. This is negative a, so this is going to move back and forth. And in describing this motion, we use such a graph. This is a sine graph or a cosine graph. As you see, there is a maximum displacement. It is called amplitude, and there is a period between two maximums. And so let's define some terms in this kind of oscillation. First of all, period is the time taken for one complete oscillation. It starts, for example, at this point, it comes to here, moves back, and then move to this position and move back to its original position. The time passed is called one period. The frequency is the number of oscillations per second. In 1 second, how many oscillations it moves back and forth? It is called frequency. And the amplitude is the maximum displacement from the equilibrium position. The relationship between period and frequency is this: T is equal to 1 over F. Let's look at some types of the oscillations. Let's start with the free oscillation. Let's define it, show it with an example. If, for example, you have a pendulum, if you release it from, if you deflect it at an angle of theta, and if you release it, it will freely move back and forth. We will call it free oscillation. Assume there is no air resistance, and it will have a natural oscillation. This is called the free oscillation. In the case of forced oscillation, let's again use the same pendulum, but in this case, we always apply a force. Okay, in this case, we force this pendulum to oscillate. Each case, once it moves back and forth, we give a force to the system, we supply a force to the system. Now here it oscillates with its natural frequency, but here the oscillation depends on the frequency of the force. This kind of motion is called forced oscillation. In the case of damped oscillation, again I am going to use the pendulum. Here we have deflected the pendulum. Assume now there is air resistance. Once you release this one freely, with the time, as the time passes, because of the friction of the air, the amplitude of the oscillation will decrease. I mean, it will initially move back and forth like this, and then at the time passes, the amplitude of the oscillation will decrease, and then at the end it will stop. This type of oscillation is called damped oscillation. Now let's look at free electromagnetic oscillations. To explain the free electromagnetic oscillations, let's look at some circuit elements. First, let's look at the resistor. If you connect a resistor to a battery, the current is going to start flowing in the circuit, but there is going to be an opposition to the flow of the current. This is called the resistance of the resistor. And there is the voltage of the battery, and there is also a voltage drop across the resistor. And the relationship between the current in the circuit, the voltage, and the resistance is described by the Ohm's law. R is equal to V over I. Now let's look at another circuit element, capacitor. If you connect a capacitor, this is a parallel plate capacitor. There are two parallel plates, and there is a voltage source here. Once you close the circuit, the current is going to flow in the circuit, and the capacitor is going to be charged. If you connect, instead of this a DC circuit, but if you connect here an AC circuit, I mean an oscillating circuit, current is going to move back and forth in this circuit. The plates are going to be charged and discharged in this case. The relationship between the amount of charges on the plate is Q, the voltage drop across the capacitor is V, and the capacitance of the capacitor is C. It is described as Q is equal to CV. And one more element of the circuit is the inductor. If we connect an inductor simply is a solenoid of wire, something like this. If you connect this one to a circuit, this is a direct current circuit. You can also connect it to an alternating current circuit. Once we close this switch, then the current is going to flow to the inductor. and once the current is changing in this circuit, there is going to be some voltage across the inductor. We will call it delta V, and the voltage drop amount of the voltage here will be equal to L times. L is a constant of the inductor. It is totally dependent on the physical nature of the coil, number of turns, so on and so forth. And L times delta I over delta T. As the amount of current in the circuit is changing with the time, delta I over delta T, then some potential is going to be created across the inductor. Similarly, if you connect this one to an alternating current circuit, current is going to move back and forth, and it will be a changing current, and a changing current will produce some voltage. Okay, now let's describe it in detail. Assume we have connected a capacitor and an inductor to each other like this. Initially, assume the capacitor is fully charged. The analogy for this electric circuit is a mass spring system. Initially, this is the equilibrium position. The mass is deflected from the equilibrium position, and now some energy is stored in the spring. Similarly, when there is charges on the plates of the capacitor, the amount of energy stored in this case in the capacitor is going to be 1 over 2 Q maximum divided by the capacitance. Then if I release this mass spring system, the mass is going to accelerate toward that direction. Similarly, the charges on the plates of the capacitor is not going to stay here forever. The electrons are going to start moving through the inductor, and we will describe it here. The electrons are going to move to the inductor, and there's going to be a changing current, and it will create some magnetic field here. The energy stored here was in the electric field, and here the energy is going to be stored as magnetic field. The analogy for this one, when we release the mass, when it passes through the equilibrium position, it will have some maximum velocity here, some maximum kinetic energy. And the energy stored in the inductor here will be 1 over 2 L I maximum square. So then this mass is going to continue to move to that direction. The energy stored here now is going to be given to the capacitor back, and I'm going to explain it here. Once more, the energy stored in the inductor will be transferred to the capacitor, and capacitor is going to be fully charged. Again, this is going to be the amount of energy on the capacitor, and the analogy here, the spring is compressed and there is potential energy stored in the spring. Then the current is going to move back to the circuit again. Once more, this capacitor is going to discharge, and all of the energy will be transferred to the inductor. The energy is going to be stored here as magnetic field. When this one is compressed, and then it will move back toward the equilibrium position, again it will have some kinetic energy here, and the amount of energy stored in the inductor will be 1 over 2 L I maximum square. Once more, this energy is going to be given back to the capacitor, and capacitor is going to be fully charged. This object is going to move to the equilibrium position, its initial position. Again, this is going to be the amount of the energy in the capacitor. Let's look at the total energy in the system. When the energy is moving between the capacitor, this is the capacitor and this is the inductor, the energy oscillates between the capacitor and the inductor. The total energy is either equal to this one or equal to this one. The instantaneous energy is going to be equal to that one. The total energy is always constant. Let's show it with a graph. The energy in the capacitor will change with the time like this, and the energy in the inductor is going to change like this. When energy in the capacitor is maximum, in the inductor it's minimum. Once it becomes minimum or zero in capacitor, it becomes maximum in the inductor. It is something like the oscillation of a pendulum again. Initially, the total energy here is potential energy. It is the potential energy. Once you release it, when this one passes through this point, it will have kinetic energy. Once it comes to this point, again it will have potential energy. So the potential and kinetic energy is going to change in this system. Again, similarly, the total energy in this circuit will change between the capacitor and the inductor. But the total energy is going to be constant. This is the E total. The total energy with the time will be constant. The period of the oscillation, and as I told you, the current is going to move back and forth between the capacitor and the inductor. Once it is oscillating, as it is oscillating, the period of the oscillation is given with this formula, and the frequency of the oscillation will be equal to 2 pi LC. So if we know the inductance L and if we know the capacitance, we can calculate the frequency or the period of the oscillation. By the way, this is called Thomson's formula. Let's look at the forced oscillations in electromagnetic waves. Now assume we have connected these circuit elements to an alternating current source, and this alternating current source, the voltage and the current of the source is changing with the time. When you only connect an inductor and a capacitor to each other and assume there is no loss of energy here, there's going to be a free oscillation of the current in the circuit. But in this case, since it is connected to a source is going to manage the oscillation of the current in the circuit. It will force the circuit to oscillate as the oscillation of itself. A similar, let me first show you the graph of the voltages across these circuit elements. As the voltage of the source is changing, the voltage in these individual elements is also going to change, but they are not going to be in phase. They will have different graphs as shown here. I'm not going to explain their details. This is the resistor, this is the inductor, and this is the capacitor. You can go to the alternating current source videos and see the explanation. So an analogy for the forced oscillation, as I described, assume here we have a pendulum. Okay, when you, as this is moving back and forth, when you apply a force, if you deliver a force each time to the system, then the motion of this pendulum will be depend on this force. Similarly, the oscillation of the current in the circuit depends on the source, alternating current source. This is called forced oscillation. Let's look at the damped oscillation. If there is no resistor in the circuit, when you close the switch, the current is going to freely oscillate between the inductor and capacitor. But if we have a resistor in the circuit, while current is moving back and forth, some energy is going to be dissipated as heat in the resistor. In this case, the oscillation in this circuit is going to be damped oscillation. Mechanical analogy for this one, if a mass spring system is immersed in water while it is moving up and down, the amplitude will decrease with the time. The amplitude of the oscillation is going to decrease with the time. This is called damped oscillation. Let's look at a simulation about electromagnetic waves, and let's go to the website. Here initially a capacitor is charged, as you see. It is connected to a voltage source, and now this is charged. And here we have an inductor. I'm going to make this circuit by closing this switch to that side, and then we will see what will happen in the circuit. The capacitance, the inductivity, resistor here is 0. There is no resistance in the circuit, and the maximum voltage is 10 volts. Let's start the simulation. Now as you see, the oscillation of this circuit, once the energy is stored in the inductor, then it is stored in the capacitor. So the energy is moving back and forth between the capacitor and the inductor. Here is the change of the voltage and the current in the circuit. There is a phase difference between them, and they are changing with the time. Let's include a resistor to the circuit and see what will happen. Let's include, for example, 20 ohm resistor to the circuit and see the oscillation. Now in this case, I'm sorry, this resistor is a very low resistor, 2 ohm. Let's make it 20 ohms. And in this case, as you see, the amplitude is changing with the time. It is decreasing with the time, and energy is lost in the resistor as heat. There is still oscillation in the circuit, but the amplitude decreases with the time, and eventually it's going to be equal to 0. So let's return to our presentation, and let's continue with solving 3 examples. If you have a 2 millihenry inductor, what capacitor should you choose to make an oscillator with a frequency of 90 kilohertz? And we are going to use our famous formula. I explained to you, frequency is equal to 1 over 2 pi LC. And from here we are given the frequency and we know the inductance, and we are asked to find the capacitance. So from here, if we rearrange this formula, C will be equal to 1 over 4 pi square F square L. And if we plug in every term, 4 pi square F is 90 kilohertz, will be 9 times 10 to the 4 square, and times the inductance is 2 millihenry, 2 times 10 to the negative 3. So making this calculation will give us approximately 7 times 10 to the negative 9, which is 7 picofarad. Okay, next question. A 2 microfarad capacitor is charged by a 50 volt power supply. The fully charged capacitor is then discharged through a 12 millihenry inductor. Find the maximum current in the resulting oscillations. We are asked to find the maximum current. I'm going to use energy conservation to locate the maximum current. We know that 1 over 2 C V max square equals 1 over 2 L I max square. From here, I max will be equal to C over L square root times V max. Actually, this formula was 1 over 2 Q max square divided by C, but if we write Q is equal to CV equivalent in this formula, we are going to get this one. Okay, so let me delete that one. The maximum current in the circuit will be equal to, the capacitance is 2 times 10 to the negative 6, 2 microfarad divided by, it is 12 millihenry times 10 to the negative 3 square root times maximum voltage is 50 volt. Making this calculation will give us approximately 0.65 amperes. Let's look at the final question. Consider a circuit containing a capacitor 3 microfarad, an inductor 5 millihenry. The capacitor is fully charged using 10 volt battery and then connected to the circuit. What is the angular frequency of the circuit? The angular frequency of the circuit W is equal to 1 over LC. Now we know L and C. They are 3 times 10 to the negative 6 times 5 times 10 to the negative 3 capacitor and inductor, and square root of these two. And if we calculate, it will be equal to 8165 Hertz. This is angular frequency. B. What is the total energy in the circuit? We can calculate the total energy by using, for example, U is equal to 1 over 2 Q max square divided by C. We know C, but we don't know the maximum charge on the capacitor. We know that Q is equal to CV. From here we can calculate the Q max. Q max will be equal to C times V max. And so the C is 3 times 10 to the negative 6, and the maximum voltage was 10. It will be 3 times 10 to the negative 5 coulomb amount of the charge. So now we can calculate the total energy in the circuit. 1 over 2 Q max square is 3 times 10 to the negative 5 square divided by capacitance is 3 times 10 to the negative 6, and this calculation will give us 1.5 times 10 to the negative 4 joules. That's it. Thank you for listening. See you next time.